All right, why don't we go ahead and get started? I'm sure we'll have additional folks start to join us. But again, for all of those who have chosen to spend their time with us this morning or this afternoon, depending on where you're joining us from, welcome. We're delighted to have you here. My name is Nathan Kuntz. I'm the CEO of Rendered.ai, and delighted to be joined here by two of my colleagues. Michael Blazej, who heads a lot of our electromagnetics simulation work, who comes out of Raytheon and has just tremendous depth in that, who's going to be doing a lot of the presentation today and demos today, and also Leo Rodriguez, who heads sales at Rendered.ai, who would be more than happy to speak with you after. We're happy to share. In terms of what we're planning to cover today, we're going to start with just an introduction to our company and our approach to synthetic data, how we think about that, and a platform for synthetic data. Then we're going to start to go into specifically the simulator that we use for synthetic aperture radar, why we think that's been important, our approach to that simulation work, and we're going to dive directly into a demo of the platform that actually you'll be able to follow along with either live or afterwards using what we call a content code, so content that we'll distribute to you, and you can feel free to try out for free. As we discuss, we'd be delighted to get questions from you. We're going to try to collect questions and then answer them at the end in this presentation. And so if you see up on the top right of your screen, there's a little Q&A tab. If you click on that, you should be able to post questions, which we'll see, and as I mentioned, try to address towards the end of the presentation. Certainly, if you have any AV issues or if you're having trouble hearing us, please let us know, and we'll try to address those as quickly as possible. But without further ado, let's jump into the content. Again, great to have everybody here. So Rendered.ai provides a platform for synthetic data. That's our product, and hopefully at the end of this, in addition to learning something about synthetic aperture radar, you'll know what we mean by synthetic data and what we mean by a platform for synthetic data. But yeah, Michael, do you mind? Let's go ahead and jump in a little further. So we really use synthetic data with our customers to address a series of different problems, and I like to introduce these first because it becomes the basis for what motivates what you're going to see throughout the rest of the presentation. And it may be some of why you're, if you're here with us, you're interested in synthetic data for synthetic aperture radar. The first is rare events and edge cases. So we see a lot of problems where maybe people have data sets, but they don't cover certain object types or certain scenario types. So we hear a lot about rare objects. Often rare scenarios are just as or more important. And it turns out it's those things that are rare that are often the most important to detect and understand. The second reason, and I think particularly relevant here with synthetic aperture radar discussion, are challenges with data labeling. So if you're using computer vision applications, you don't just need a data set, you need a labeled data set that can tell your algorithm what it's looking at. And that can be really difficult to do with synthetic aperture radar because it's hard for a human being without ground truth information to necessarily know what's in the image. The third reason, and actually part of the genesis of our company, is that increasingly it's not even human eyes that look at the imagery that's being created. It's really just artificial intelligence and computer vision algorithms that are processing that imagery. And that creates a really interesting systems engineering problem for the next generation of sensors, the next generation of satellites, right? How do we decide how to design those satellites? Maybe in the context of SAR, what matters more? Cross range or range resolution versus signal to noise, not to a human's eyes, but to an AI trying to make a detection. Historically, that required building up a full system, launching it, collecting a massive amount of data, labeling it, and really what that has eliminated in a lot of the AI workflows is the ability to do model-based design, which is what we expect from really every other form of engineering. And then finally, we work with a number of customers that are dealing with either high risk or secure data sets. That can be in the medical industry where there are PII concerns, or defense and aerospace where there are security concerns. Let's keep going, Michael, if you don't mind. And if you could click through so that we get this full slide up. There we go, perfect. So the other thing that shows up beyond those pain points, which often drive people to synthetic data in the first place, is that in computer vision workflows, the conventional approach leads to this very linear engineering process, where initially we acquire large volumes of data, we train an algorithm, we can do some hyperparameter tuning and tweaking. We test that, and then we sort of get to accept or reject that result. It's very difficult, like in a typical software workflow, right? If the code wasn't performing to spec, you would go back and rewrite the code. But in the world of artificial intelligence, right, the software's behavior is not defined by code. It's defined by the data that's used to train it. And so you can't just go back and rewrite the data. With synthetic data, when we begin to simulate those data sets, that actually does change that paradigm, where suddenly you can get a certain level of control over at least some of the data that's being used to train that algorithm. And that really, it's more than just sort of incremental improvements that can really change the ways in which we engineer these systems. Okay, let's keep moving. So if you start to get into synthetic data, or if you've already gotten into synthetic data, it's really natural to begin your exploration by focusing on the simulation technology. And we're going to spend a lot of time talking about simulation technology today, so that would be appropriate. But I think it's also worth reflecting on the differences between that sort of simulator focus and what it really takes to be successful. Right, if you enter into synthetic data and you say, hey, I just need a great simulator, and then that's going to give me a great synthetic data set, and that's going to result in a great AI model, you miss a lot of really foundational work that's required to be successful. And there's a number of reasons for that, but I think part of it is, and it's helpful for all of us to realize, that synthetic data itself is very rarely, if not never, an actual outcome that people want. It's not that the synthetic data itself has value. What we're trying to achieve almost always is some form of algorithm improvement, AI improvement, insights into what's being engineered. And that has a very different implication in terms of the total number of tools. And we can start with, hey, we're not just simulating one thing. We need to simulate tens of thousands of examples. We need to create those varieties. They need to be highly diverse in order to span the space. That means we need to be acquiring assets. We need to be using things like procedural generation technologies, and those need to be pipelined to a simulator. All of that type of work has typically been the provenance of talent that would be sort of modeling in sim or Hollywood style capabilities, and in the context of synthetic data, we call these people synthetic data engineers. Important to understand, those are very different skill sets. Doing that well is a very different skill set than what a typical data scientist would have studied for. In fact, we find that there's almost no Venn diagram between them. And so if you're building out that capability, that also implies you need to have some mechanism to deploy those tools to the people that need them, to the computer vision staff, data scientists that are actually going to be using that data. Typically, the compute requirements are such that that needs to be deployed into a high-performance compute environment, and then that system needs to be taskable by the engineering staff that need access to the data. So there's some sort of deployment capability required. There's a managed compute environment needs to be set up. That deployed capability needs to be taskable in a way that maps to the types of engineering that the data scientists need. And then the data that comes off also is not just intrinsically useful. We have to do things like assess its quality, understand, are we mapping to the real world in a way that's going to be meaningful for AI training? In the parlance of AI, we might say, are we getting good latent space coverage? There are sort of classic post-processing and domain adaptation tools that are often used. And then other ways in which we want to leverage that to generate AI models, not just necessarily training on synthetic, but combinations of real and synthetic, or maybe bootstrapping on synthetic, and all of those workflows benefit from having infrastructure in place. And so just to kind of round this out, there's a lot more steps and really at least 3 different types of users that end up being involved when you start getting to effective synthetic data generation. So not just the modeling and sim community, but a cloud capability and then data scientists, and we need to get those all working together. So if we can keep going, Michael. So at Rendered, what we've done is we've built out a platform to facilitate exactly that workflow. And so if you kind of map the steps all the way from content generation to AI pipelining, we've done and continue to add to just a suite of tools that help every single one of those processes along the way. And that forms our core product. And you'll see Michael will be demonstrating using the graphical user interface to our platform today. So you'll get a good sense of what that looks like during this webinar. But of course, that's just a platform. On top of that, we have to put content that's relevant for different types of problem sets. And so the way that we're structured as a business is either our customers can build out that content and deploy that to our platform, or third parties can, but we also have a team that builds out different types of content, does simulation tool integration into the platform, and provides those as a capability. And so the tools that we're going to show today, the application we're going to be sharing today, are some things that we've built internally at Rendered and think are important, can play an important role in the marketplace here. But I wanted to share, it's sort of, it's not that we are a synthetic aperture radar simulation company. We think of ourselves as a synthetic data platform company. That's really our focus. And then we have built out some synthetic aperture radar tools on top of that platform that we think are particularly useful and interesting given what's happening in the commercial SAR space right now. Okay. So with that, I'm going to turn it over to my colleague Michael to really dive into more about synthetic aperture radar. We'll do a brief background and before getting into our demo. Hey, Michael.
Hey, Nathan. Thank you very much for the introduction. So my name is Michael Blase. Yes, I've been dealing with radar for quite a while. So let me step right into this. So radar and SAR. Most radars operate in the 100 megahertz to 30 gigahertz range, but there are other applications, other special applications that go above and below this range. We have this optical system example here in frequency because there are optical systems in satellites, but you can see that the frequency range is very different, which is why they typically document them in wavelengths, because it's just much more manageable. The benefit for a lower frequency system is that it doesn't interact with the small objects in the air that typically attenuate optical systems a lot more. Rain, snow, leaves, fog, and clouds, even smoke. SAR is able to see through these things where optical systems they just see the smoke. And a benefit of active systems, which radar is that it can image the Earth at night, which half of the Earth is only illuminated at one time. And I mentioned clouds. 67% of the Earth is at any one time is covered by clouds. And these aren't always mutually exclusive, and they definitely overlap. But that does inhibit the capability of optical systems to see objects on the surface of the Earth. One other benefit that radar has is that it's extremely accurate as a range measurement system, and so it's ideal for change detection. We've seen this with just changing Earth structures over time. And so radar is a radio detection. It stands for radio detection and ranging. And SAR is the application of radar to create a synthetic aperture. So how do you create a synthetic aperture? well, you have a platform. In our case, it's typically a satellite, but it can be on an airplane as well. And it transmits a signal. And it transmits a signal to the target. And effectively, what's happening is that this target is represented by scatters, surfaces, corners, metal, glass, rubber. All these things reflect the signal back. And so what this one signal does is it takes a cross section, a range cross section of this target. And that's just one signal. What the radar then does, oh shoot, I'm sorry, I clicked on the screen. What the radar then does is it flies across the sky, and it does the same thing over and over and over. And so it takes many cross sections of the target. And what we're able to do is combine those into a radar image. And images aren't typically compressed until all the data is recorded, but this is a really interesting example that we've done where we've tried to compress the image from each pulse that's gathered in the dwell. And so you'll see the video as it plays. The image is captured here on the left side, and on the right side, you'll see as the image is completely captured, the compressed image, the resulting image, the quality of it just gets better and better and better. And so you'll see right in the middle is where we hit the target for real, and all of these things come into view. But even before we get to the main target, you can start to see these aspects of these things show up. And it isn't until we get past the main thing that we really start to get this really nice image, a compressed image showing up. Let's see. Now these are real measured SAR images of a tractor and a tank from the SAR dataset. But the SAR images are highly dependent on the angle of incidence. And so, and the angle of incidence being, I just want to show an example of this, is that if a satellite is flying by, the look angle to the target is this angle right here. I've seen examples of anywhere from 30 degrees to 70 degrees. And so this can be a very steep angle. And you can be looking at a target from very different angles. What happens there is that, I apologize, that I did not mean for that to happen. What happens is that the objects in these scenes end up looking very differently than they would from 30 degrees to 70 degrees, and even from a tractor to a tank. It can be hard to tell one from the other. So that's where the benefit of simulation comes in, because if you were to try and capture a real data set on one target at all aspect angles and all look angles, that would be extremely expensive. It would take you a very long time and prone to error and noise and all those other things that you can kind of remove when you build a simulation. So why did we build a simulation? Electromagnetic simulations have been around for a very long time, but a SAR simulation requires a lot of simulations. I think a number of you have seen this video that was posted on LinkedIn. This video consists of about 180 different images of a cargo ship. Each image required, I believe, 2,000 different geometry simulations. And so we're talking about massive amounts of electromagnetic simulations. And you have to re-simulate that at each geometry. So we came at the problem with the need to generate a significant amount of data like this in a few minutes. And there are trade-offs in doing that. You don't get the full, there are certain aspects of electromagnetism that aren't captured, but the 0th order, the 1st order, and some of the 2nd order aspects are. We capture polarization, diffraction, polarization dependent reflection. We cover antenna models and a number of other things that I'll cover on the next slide. The reason that CGI tools aren't able to support this is because they don't support energy propagation models. You can apply a texture to a surface, but the energy reflected from that surface, whether it's a metal or a plastic, whether it's smooth or rough, is very different depending on those properties. And so thousands of EM signals are required to produce an image. And so we decided that a new tool was needed. Now, I'm not going to read through this whole slide. I'd like to point out that it really isn't that hard to get a SAR image of something, as long as you have a 3D model with 2D triangular meshing structure facets and surface materials applied to that structure. Once you have that, we have all the other things to define a radar and define the type of image that you're trying to generate. Another thing I will point out is that we use a physical optics, and we track all phase delays to every object in the scene. So, and that is how we do our electromagnetic simulation. We also have started on the CPU side, but we've accelerated our simulation with the GPU using the CuPy library. You can see in the top that the electromagnetic simulation alone was improved by about 100x, and then when it's included in the full computation, which includes the image formation processing for post processing, it's improved by 5x. So there are still many more optimizations possible to increase the speed of generating synthetic SAR images. And this is really important because we're trying to generate thousands, sometimes tens of thousands of images, because these AI ML models are very data hungry. So I'm going to show you a demo now, and you can all follow along or follow along later by using this SARDEMO content code. And I'm going to show you, this is the dashboard that you get dropped into once you create an account on Rendered.ai and use the SARDEMO content code. You'll have a workspace, and in that workspace, you'll have a number of graphs that I've already created for you, and some data sets that I've already created as well. For this example, we're just going to create a new graph to show you the process of doing so. So create a new graph. We're going to call it AndyMax2. It uses the SAR channel. If you'd like, you can give it a description. So let's create. And once that comes up, let's see. We pop this open, and this is where your nodes are available. You'll see a SAR. You'll see some SAR over here, and provider. And so this is how we create the radar. That's it. That defines the radar. We can create scene and generate the images. So we need all of these. And for this one, we are going to model the HandyMax. We could pull any one of these. Now, to place this model, we'll need to set its position. And so this generates a model, a ship, that goes into the objects. We can control the position and the rotation of the object. That object goes into the create scene. Now, it is possible to have more than one object go into this scene. And eventually I'll have background options that the user can select from, whether they're ocean or desert or grasslands, etc. But right now it's just a target. We take the radar config and we drop that into the node that tells you to generate images. We have our scene. We put that there. Now, what this does right now is it generates a single image. And if you ran this 10,000 times, you get the same image over and over. What we want to do is get images of this target, you know, rotated in azimuth and at different look angles from the satellite, right? So what we'll do is we'll generate a two-dimensional sweep, and we'll need some vectors. So the y value we're going to use to generate a yaw effect. So since this is going to the rotation node, the rotation is controlled by a roll, pitch, and yaw. So z in this case is the yaw, and for the other dimension, we're going to sweep the look angle, which, as I showed you before, is the angle that the radar looks down at the target on. So we want the look angle to go from 30 to 70 in 1 degree steps, and we'll go from, and we want the y-axis, which controls the yaw of the ship, so we want that to turn all the way around. We want to start from 0 and go to 360 in 2 degrees in 1 degree steps. And this is the full. This is it. This is this is how you create a two-dimensional sweep of a target. You can give it a name. You want to make sure that you give it the right frequency, which I haven't done. You can specify the polarization, the transmit and receive polarization of the target. So typically people will do copol, HH, or VV, but in some cases I've seen cross-pol systems, and so those are available as well. Currently, strip map is the only mode we support, but I'm working on adding spotlight and sliding spotlight. And if you have a range resolution in meters or an azimuth resolution that you want to specify or change, you can put that here. This was now for the people who are radar experts in the room. I could have exposed a lot more parameters, but these are available from metadata that you can download from Capella or Umbra or any of the other SAR providers that are out there. Actually, I think there's only 2 or 3. And so if you know nothing else about radar, about SAR, you can look at the metadata for that image, fill out these parameters, and generate some SAR data. This entry right here lets you specify how big of an image you want to generate. We're going to leave it at 500 by 500. And once this is done, you click Stage. It'll tell you to go to the jobs view and generate a data set using the graph. And you'll see this right here. And we can type in, 1,000. I'm not going to do that. I'll click Run, and we'll do some magic cooking movie stuff, and I'll show you that I've already downloaded all that information. And what you'll see here, let's just maximize this so you don't have to stare at my screen. What you'll see here is a picture of the Handymax. Now this isn't obvious to anyone looking at it that this is a Handymax, so let's bring up the actual Blender model. And I would, since I've looked at this a whole bunch, a lot more than you guys, I would say that the superstructure for the Handymax is this thing right here, right here. You have this crane structure in this area, and I'll try and zoom in there. You have another crane structure here, and in the Blender file, you can see these crane structures. Now I've set. Now we could pick some different images to look at, right? But we can go back to the Blender model and say, oh, all right, yeah, this is starting to look a little bit more like what I like. This kind of makes sense. If the radar is up here, it's trying to image this superstructure in these cranes right here. And you can see a couple other scatterers in the scene that aren't obvious as to what they are, but they're part of the signature of this target. And that is the demo. Nathan, if you want to come back on, I think we're doing pretty well.
Yeah, thank you, Michael. So just to recap here, so Michael shared a little bit about our simulator, the fact that we have built one that takes into account the needs for synthetic data and some of the approximations that we made in order to reach the speeds that allow us to generate data at volume. And then dove into a use of the platform that you you're welcome to reproduce as well using that content code, SAR code, and we'd be happy to walk you through exactly how to use that. But if you sign up for an account on our platform at www.rendered.ai, you'll see the ability to add a content code at sign up time. So at this time, I think we wanted to open it up for questions. If there's any questions coming in from the group. So far, it's been somewhat quiet. Okay, I see some hands going up. If you wouldn't mind putting your questions into the Q&A, let's make sure we've got that working. If you can type them in. Are people able to type into the Q&A? I just want to make sure that we don't have a technical challenge here.
I think we've locked chat, and so if they can't post Q&A, oh, there we go.
Okay, excellent. Yeah, thanks for getting us started, Rustam. How can we help?
I can show a little bit more about the process that's happening that I kind of skipped with the movie magic until a question shows up.
Why don't Michael? Would you mind showing how to create a workspace?
There's the question from. Sorry to interrupt. There is another question from Adam Schneider.
Okay. Okay. So yeah, go ahead, Michael. Why don't you?
The question is, do we have different ship types? Yes, we do. We have, I think, in the graphs that I pulled up. I probably did it too quickly, but we have 5 ships in the example, and we have many more in our database. Really, getting a model is not hard. It's applying the right material properties to the right areas. Excuse me, which is a little bit time consuming. If you're looking for background conditions like ports, that is not a hard thing to do. We really just have to have more models of those structures. As I said, you can add more than one object to this create scene. So if you have a model object of a port, then you can include that. It will definitely increase your runtime, as I'm sure you're aware. Now, backgrounds, I don't have that just yet. And as you can see, I think I mentioned that I'll be adding backgrounds to this create scene object very soon.
So why don't I jump in on this next one about simulating pavement? The answer is yes, we can simulate pavement. And just for the group that may not be familiar with some of the challenges with that, so pavement has sort of a micro granularity to it. So it's a rough surface, and the reflections off pavement behave very differently than reflections off, say, a smooth metallic or dielectric surface would be. And so you actually have to be really careful about how you simulate something like pavement electromagnetically, because you don't necessarily want to mesh all of the microstructures across that surface. And so if you look at a typical SAR response, in fact, what you see is surfaces like pavement look almost smooth in images. And the reason is what you're picking out is what's called the Bragg resonant reflections off of that rough surface. And we model exactly that. In fact, if you get into the way that our 3D models are provided into the platform, each surface has a conductivity, permittivity, permeability, but also a roughness character that tells us how much of that Bragg resonant response to include for that facet. So Michael, maybe you can share a little bit about how we think about taking a 3D object and modifying it. I don't know that this channel has modifier nodes in it. You might bring up a different one to show how we think about that in the context of this, different configurations of a cargo ship.
Correct. So the modifications that are supported in this channel are really just position and rotation, and one more, which is by changing the object scale, so you can make it larger or smaller. There are other channels which actually I'd rather not go into because I don't have a whole lot of experience with those channels. But I know other channels support adding rust to things and changing materials. Now, if you're looking at different amounts of cargo on the ship, I'm not sure if that exists now, but that's not a hard thing to do. That's a procedurally random generation thing that is fairly straightforward.
Yeah, maybe that's worth highlighting as we talk about kind of how we engage with companies in different applications, and I think speaks actually to Rustam's comments here about different types of content. So one of the things we've been intentional about with our platform is not trying to start with all of the content that everybody needs all at once. So we've built out this platform suite of tools that are really appropriate for really whatever you're doing in computer vision with synthetic data. But from there, we work with our customers to understand specifically what they need. So, Rustam, if you're pursuing a SAR program that needs different types of objects or has particular backgrounds that are necessary, then we would work with you to define the scope of that content and build that out for you, or allow you or teach you how to do that if that was something you're interested in pursuing. But because we can't build that for kind of everything under the sun, we end up doing that on a case-by-case basis. Scott, yes, we do. We support both co-pol and cross-pol scenarios. So Michael's showing them there. I think in this kind of limited interface, we're doing that where you select one. It can also be structured behind the scenes. That can be structured to capture multiple polarizations in a single run. So Leo, why don't we turn it over to you to share a little bit about what people can do if this seems interested and what they should do in terms of reaching out.
Absolutely. Can you hear me okay?
Yeah.
Yes, perfect. That's my favorite topic. So thanks, Nathan and Michael. Great job. Really appreciate it. And more than that, thanks to our audience for sticking with us throughout the session. I can see many of you coming from different parts of the world. Some of you might be deep in the night and very early in the morning. So we're very appreciative. We know your time is extremely valuable, and we're very grateful that you chose to spend 45 minutes with us. Just to kind of close very quickly, if you are an Earth observation company or a system integrator or a government organization or even a consultant, and you're working with SAR content or any other Earth observation content, you will face some of the challenges that Nathan and Michael talked about today, particularly on enlarging and expanding your data sets. And synthetic data and Rendered.ai are becoming rapidly an alternative for that to solve that problem. So I hope you enjoyed it. I just want to remind everybody that about the content code. So the content code is a little token. It's a word that you've seen in the screen. I'll just repeat it here for everybody. It's called SARDEMO, SARDEMO. It's one word. It's all caps. And that's a content code that you can add into the platform when you're signing up, so you can see all the content and play with it for free for a limited time and play with that. But our ultimate goal is really to have a conversation and to kind of understand your background, what you're working on. If you contact us, there's going to be many ways to contact us, but if all else fails, you can write to sales@rendered.ai, and either myself or somebody in my team will pick up the email. Rest assured, we're all engineers here, so it's not a hard sell, but just to understand where you're at with your project, how we can help. We'll tell you no if it's not a fit. I'll personally commit to make my biggest effort to get Mike on the phone. Mike is very busy developing our SAR capabilities, but I'm sure he will be happy to have a one-on-one conversation, understand your background and how we can help you. So with that, I'll wrap it up. There is a couple more questions. Do we have a few minutes for a couple more questions? We have 3 minutes. And there's one from Adam that says, I know this is a presentation about SAR, but can you also render synthetic data like these for optical imagery? I think softball to Nathan.
Yeah, so we handle a wide variety of different simulation types. From a satellite perspective, we do RGB. We also have a partnership with Deers Lab out of RIT to handle multispectral, hyperspectral, and really high fidelity optical simulations. We've been excited about that, seeing great results from that partnership. And just to again refresh, our approach here is not that we've built a platform that is specific to a particular domain, but rather we provide this suite of tools. Michael showed some of them in terms of how you can configure jobs, kick them off really quickly, get an HPC cluster up and running to generate large amounts of data, and then get a data set on the back end. So we do that. And then work with people to get the right simulation technology for them deployed onto the platform. And that's really what Leo is highlighting. So that's why we'd be delighted to chat if we can help you guys out.
Well, with that, thanks Nathan and Michael, and thanks everybody for staying with us. We'll share a recording of this and the material very, very soon. Until next time.
Thanks everybody. Thanks for joining us.